At first glance, it seems like nothing more than another breathtaking view of the night sky. Countless points of light fill the frame, nearby stars shine in the foreground, and an endless backdrop of distant galaxies stretches across the darkness. But this image represents far more than a beautiful photograph. It marks one of the earliest observations from an observatory built to transform modern astronomy. With the Vera Rubin Observatory beginning its scientific mission, researchers are entering an era where the universe can be studied on a scale that was once impossible. The significance of these first observations goes well beyond producing sharper images. The Rubin Observatory has been designed to create an enormous, continuously updated record of the sky. Instead of collecting isolated snapshots, it repeatedly surveys vast regions of space, allowing astronomers to watch how the cosmos changes over time. For the first time, the night sky can be monitored almost like a living documentary, revealing events that unfold across days, months, and years. To understand why this observatory is so important, it helps to appreciate its extraordinary engineering. At its heart is the largest digital camera ever constructed for astronomy. Containing roughly 3.2 billion pixels, the instrument is about the size of a compact automobile and weighs several tons. A single full-resolution image contains so much information that displaying it at its original quality would require hundreds of ultra-high-definition screens placed side by side. Yet the remarkable size of the camera is only part of the story. Its real purpose is not simply to capture impressive photographs but to scan the visible sky over and over again. By comparing one observation with the next, scientists can identify objects that brighten, fade, move, or suddenly appear. Every observation becomes another frame in an enormous time-lapse record of the universe. One of the observatory's earliest composite images immediately demonstrated this capability. What first appears to be a simple collection of galaxies soon reveals astonishing complexity. Nearly 10 million galaxies are packed into a single field of view, each representing a different chapter in cosmic history. Elegant spiral galaxies display graceful rotating arms filled with young stars, while massive elliptical galaxies glow with the softer light of ancient stellar populations. Others show clear signs of dramatic collisions, their structures stretched and distorted by immense gravitational forces. Closer to home, stars from the Milky Way appear scattered across the same image. Their distinctive diffraction spikes are created by the telescope's optical design rather than by the stars themselves, adding recognizable patterns to the brilliant points of light. The result is an extraordinary perspective where nearby stars and galaxies billions of light-years away exist together in one enormous cosmic panorama. Equally impressive is the speed with which this achievement was made possible. The massive image was assembled using more than 1,000 separate exposures collected over only a handful of observing nights. Combining these observations produced a field both deep and wide, demonstrating that the Rubin Observatory can survey enormous portions of the sky far more efficiently than previous generations of telescopes. This efficiency represents a major shift in astronomical research. Earlier observatories often required long observing campaigns to capture similar depths over much smaller regions of the sky. Rubin's design allows scientists to gather vast amounts of information at an unprecedented pace, dramatically increasing the number of discoveries that can be made in a single observing season. Among the first featured targets was part of the Virgo cluster, one of the nearest large collections of galaxies beyond our own local group. Roughly 55 million light-years from Earth, this region showcases an incredible diversity of galactic forms and evolutionary stages. Within a single image, astronomers can examine galaxies actively creating new stars alongside others whose periods of intense star formation ended billions of years ago. Some systems shine with brilliant blue hues, evidence of massive young stars illuminating their spiral arms. Others display warmer golden and reddish colors produced by older stellar populations that dominate mature galaxies. Together they provide a striking visual timeline of galactic evolution, revealing how different environments shape the lives of galaxies across cosmic history. One prominent object in the image is Messier 49, a giant elliptical galaxy containing vast numbers of ancient stars. Nearby lies NGC 4535, an elegant face-on spiral galaxy whose bright arms continue to produce new generations of stars. Surrounding these well-known systems are countless dwarf galaxies, faint spirals, and distant elliptical galaxies, each contributing another piece to the immense structure of the universe. The deeper the image is examined, the more hidden treasures emerge. Beyond the Virgo cluster itself lie countless background galaxies so distant that many appear only as tiny reddish points of light. Some of these remote systems are located more than 1 billion light-years away, allowing astronomers to observe light that has traveled across an enormous fraction of cosmic history before finally reaching Earth. Perhaps the most dramatic feature captured in the field is a remarkable triple galaxy interaction. 3 galaxies are caught in the slow process of merging under the influence of gravity. Their once distinct shapes are being pulled apart, forming long tidal tails, luminous bridges, and distorted arcs that reveal the tremendous forces at work. Although these collisions unfold over hundreds of millions of years, the observatory captures a single moment within that immense cosmic transformation, offering a glimpse into one of the universe's most spectacular evolutionary processes. Even while the observatory was focused on the distant universe, our own solar system quietly left its signature across the images. Thin streaks of light crossed the field, created by asteroids moving through the camera's long exposures. Rather than being unwanted flaws, these trails became valuable scientific observations. Advanced processing software can separate these moving objects from the stationary background of galaxies, producing a clean final image while simultaneously recording the paths of newly detected bodies. This capability highlights one of the Rubin Observatory's greatest strengths. During only about 10 hours of early observations, it identified nearly 2,100 previously unknown asteroids. That number is remarkable when compared with the pace of traditional asteroid discoveries. What once required many observatories working throughout an entire year can now be accomplished on a dramatically shorter timescale. The impact of this achievement extends far beyond setting new records. Scientists currently know of roughly 1 million asteroids throughout the solar system, but Rubin is expected to increase that number by several million over the coming years. Every new discovery improves our understanding of how the solar system formed, how its smaller objects evolve, and which near-Earth asteroids deserve careful monitoring. This means the observatory performs 2 very different jobs at the same time. It can observe galaxies located billions of light-years away while also tracking faint rocky objects traveling within our own cosmic neighborhood. Few astronomical facilities have ever combined such wide-ranging capabilities into a single instrument.